All right, let's take a look at the limit and their properties of section 2.4 on the infinite limit. So the objectives are to determine infinite limits from left and from right, and find and sketch the vertical asymptotes of the graphs of a function. Infinite limit meaning you have a limit as either positive or negative infinities. That's what it means. Now let's say that f be a function given by 3 over. So f of x equals to 3 over x minus 2. Okay, so that's our function f of x. And you can see that f of x decreases without bound as x approaches 2 from the left, and then f of x increases without a bound as x approaches 2 from the right, and we call this x equals 2. Actually, it's called the vertical asymptote. Okay, so as you can see, in terms of limit, when we make the f of x approaches 2 from left, from this side, from left, you see the limit becomes negative infinity. So limit x approaches 2 from left for 3 over x minus 2 becomes negative infinity. And limit x approaches 2 from the right hand side for 3 over x minus 2 actually is positive infinity. If you look at it from the graph, on the right hand side going this way, you see that it's getting bigger and bigger. So limit and that approaches 2 from the right becomes positive infinity. Okay, so this is a summary of what we just discovered. Behavior is denoted as limit f of x decreases without a bound as x approaches 2 from the left, and then f of x increases without a bound as x approaches 2 from the right hand side. So create a table to investigate the limit, and the table actually confirm whatever we see from the graph. Right, when we have a f of x decreases to negative infinity when we approaches 2 from the left hand side, and then from the right hand side f of x increases to positive infinity. So the limit actually does not exist, and this is what they call infinite limit. Since the infinity is an unknown number, so nobody knows what that is, that's why it does not exist in some sense. The limit in which f of x increases or decreases without a bound as x approaches c is called an infinite limit. Okay. So definition of infinite limit, that f be a function that is defined as every single number in some open interval containing c, except possibly as c itself. The statement that when x approaches c for function f of x equals to infinity, and that's what the infinite limit is about, right? So as you can see, right, in this particular graph, you will see that limit will, from left hand side of the c, and from right hand side of c, limit becomes positive infinity, right? Limit when x approaches c for f of x equals to infinity, positive infinity, and this is what they call infinite limit. Okay. And this is also two more examples about the infinite limits from the graph. So on the graph A, the function is f of x equals to 1 over parenthesis x minus 1 parenthesis square. As you can see, when x, this is 1 right here, x approaches 1 from the left, the limit is from left, limit for f of x is equals to positive infinity, and limit when x approaches 1 from the right on this side for f of x equals to also positive infinity, and that means the limit does not exist, right? So we have an infinite limit. Occurs at x equals to 1. And this is also what they call asymptote, right? This dashed line is called asymptote. Alright, let's take a look at the graph B. And this is another function which is f of x equal to -1 over x minus 1. So as you can see, when x approaches 1 from the left, limit for x approaches 1 from the left, in this case is positive infinity, and limit x approaches 1 from the right is actually negative infinity. If you look at the graph going this way, the graph decreases without a bound, so infinite limit infinite limit occurs at x equals to 1 as well, right? So both of this is also the asymptote we are talking about. This is the asymptote. Okay, so when x approaches 1 from left and right, this is just x minus 1 square is a small positive number. So the quotient 1 over x minus 1 square is a large positive number, and then f of x approaches infinity from either side of x equals to 1. So you can conclude that limit for 1 over parenthesis x minus 1 square x approaches 1 is equal to infinity. Okay, and the graph confirms the analysis. Similarly, for the second example, the quotient of -1 over parenthesis x minus 1 is equals to positive negative infinity, right? If from left hand side it's positive infinity, from right hand side it's negative infinity. So the limit does not exist. As you can see from right hand side, it's negative infinity. And the graph confirms our analysis, right? This way and this way. And next thing that will lead us to a vertical asymptotes, right? So infinite limit results in vertical asymptotes v dot a. This is an abbreviation for vertical asymptotes v dot a dot. If it were possible to extend the graph in figure 1.1441, positive and negative infinities, you could see that each graph becomes arbitrarily close to the vertical line, x equals to 1, and we call this vertical asymptote. This is vertical asymptote, and this is vertical asymptote, the dashed line, right? This dashed line, this dashed line. Okay. And this is basically the definition of the vertical asymptote. The graph becomes arbitrarily close to the vertical line. Okay, that vertical line is the vertical asymptote. So definition of vertical asymptote is if f of x approaches infinity, positive infinity or negative infinity as x approaches c, from the right on the left, and the line x equals c is a vertical asymptote of the graph of g of f. Vertical asymptotes, let f and g be a continuous on an open interval containing c. If f of c is not equal to 0, g of c is equal to 0, and that exists on an open interval containing c such that gx is not equal to 0 for all x is not equal to c in the interval, and the graph of function is given by h of x equals to f of x over g of x, has a vertical asymptote at x equals c. Right? So let's take a look at this. Determine all the vertical asymptotes of the graph of each function. So you have to find the vertical asymptotes. You just set denominator equal to 0. So setting 2 times parenthesis x plus 1 equal to 0, and solve for x. So divide 2 from both sides of the equation, cancel that, x plus 1 equals 0, subtract 1 from both sides of the equation, x equals -1. So x equals -1, that's our vertical asymptote. And for b, this is a. For b, similarly, you just set in order to find a vertical asymptote, you set the denominator equal to 0. Okay, so factor, we can add 1 from both sides of the equation, cancel that, x squared equals to 1. Then we take the square root from both sides of the equation, and then when you take the square root on both sides of the equation, you have to put positive and negative. On the right hand side of the equation, so square root of x squared becomes x, and we have plus minus square root of 1 becomes 1. So x equals plus minus 1, that's our vertical asymptote. In this case, when x equals -1, the denominator of f of x is 0, and the numerator is not 0. So by theorem 1.14, you can conclude that x equals -1 is a vertical asymptote. Okay, this is our vertical asymptote. And by factoring the denominator, you can see that denominator is 0 at x equals -1 and at x equals 1. So x equals -1, and this is x equal to 1. They are both vertical asymptotes. The c and l be real numbers, that f and g be functions such that limit for function f of x when x approaches c equals infinity, and limit for g of x when x approaches c equals to a constant l. Sum of differences. So when you add the two functions, limit is still infinity. When you multiply both functions, limit is still infinity. It's very easy. We can easily prove this, right? We can just separate into two different limits. And the first one is infinity. Infinity plus minus a constant, still infinity, right? So this is a quick proof. And this one, separate into f of x times limit x approaches c for g of x. We have infinity times L, still infinity. In this case, when L is greater than 0. When L is less than 0, then it becomes negative infinity, right? The third one is a quotient. So in this case, we separate into limit when x approaches c as g of x. That's on top. On the bottom, we have limit x approaches c f of x. So we get a g of x is L over infinity. Constant over infinity becomes 0. That's why for the quotient, the limit when x approaches c for the function g of x over f of x becomes 0. Because limit when x approaches 0 for the constant function 1 equals to 1, limit when x approaches 0 for the function 1 over x squared equals infinity. When you combine them, it's still infinity, right? 1 plus infinity is infinity. Still infinity. Because limit when x approaches 1 from left for the function x squared plus 1 equals to 2. Limit for cotangent pi x when x approaches 1 from left is equals to negative infinity. Then you can write limit when x approaches 1 from left for x squared plus 1 over cotangent pi of x. This is the same thing as writing 2 over infinity, and that becomes 0, right? Any constant over infinity becomes 0. Because limit for constant function 3 when x approaches 0 on the right equals 3. Limit for cotangent x when x approaches 0 from the right is infinity. When you multiply them, you still end up with infinity.